To this point, and most of us, we have been using something called a Celsius scale and Fahrenheit scale. And all of this are based on water as a benchmark and its behavior, because water is important to us. That's the very first thing that we need to study. Of course, we have gone beyond that point. Now the science and the civilization has advanced to an extent. We're not just talking about water, we're talking about many things. We're talking about outer space also, deep sea as well. There are many things that we are studying. We're studying about things which we can't see with our naked eye, right? So when we are doing such research, having water's benchmark as the starting and the ending point is not going to help us, or it won't help us with our curiosity. So that's where our absolute zero and absolute temperature scale and all of this comes into picture. So to understand temperature at a deeper level, we need a scale that connects directly to how much energy atoms and molecules actually have. That's where the temperature idea comes into picture, right? So that's where the absolute temperature scales comes in. At any temperature above something called as absolute zero. Okay, what is absolute zero? I'll explain. So it's written over here. Every atom, it can be from solid, liquid or gas, they're always vibrating or moving. More the temperature, faster the motion. Less the temperature, slower the motion, right? So let me talk about this. So what we are looking at is, we are looking at something called as absolute zero, right? If this is a starting point, as in when I move to the right, say this point and this point, so this will have less motion compared to this. The atoms will be vibrating more over here. Here the movement is more. So this is your temperature. So as and when the temperature increases, the movement increases. Lower temperature is slower compared to this. So this you guys know of, right? So temperature is basically a measure of internal motion. So temperature is a measure of internal motion. Agree? Okay. Now, if things keep reducing, don't you think at certain point of time altogether the motion stops? And that's your absolute zero, as simple as that, right? When I move to the right, the movement increases. When I move to the left, the movement decreases. But at a certain point of time, or a certain temperature in this case, it has to come to a stop. And that is your absolute zero. So atom have the least possible energy at absolute zero. Molecular motion drops to the minimum allowed value by physics. The system cannot be cooled further down, basically. So in all of this way, I'm just telling the same point. It is the coldest value or the lowest value in terms of temperature that we know of as of now. So absolute zero is around 273.15 degrees Celsius. Just a second, let me check that. Yeah. Did I write minus? Oh, sorry, not positive, negative, my bad. So this is your absolute zero. Okay guys, so this also is written as 0 Kelvin. So that is something that we'll be introducing now. So can we go below 0 degrees Celsius? No, we cannot go below absolute zero as of now, right? I mean, I can tell never, because you can tell never in nature. There's always something that we dig in the future and we find something else. I mean, that's my thing. But yeah, let me not, there's nothing that I'm trying to imply over here. I just want to tell, as of now, it is a no. We can't go below 0 degrees Celsius. Okay. So because the temperature measures energy, and as per our definition and idea, this is the least energy it can have. So if you have the least energy possible, you can't have lesser than that, because that's the least. It's like telling in my bank account I have 0 rupees. So tomorrow I have lesser than that. It's not possible, of course, without us taking loans and all that. That value is not possible. So that's it. So that's your absolute zero. So let me read through and make it more clear. So these are some of the things that we need to know. Absolute zero, there's a new scale that we are getting introduced to, that is your Kelvin scale. In terms of degree Celsius, it will go to this value. In terms of Fahrenheit, it will go to this value. And these are your set of formulas that will help us reach that calculation or calculated values. So all of this you have to know. And you have 0 degree Celsius in terms of Kelvin and in terms of degree Fahrenheit. Okay, this is what we are learning here. What is absolute temperature? So first is we need to talk about problem with Celsius. Celsius scale is based on 2 arbitrary points, that is 0 degrees Celsius and 100 degrees Celsius, the freezing and the boiling point of water. These values have nothing to do with the molecular motion, but temperature has to do with molecular motion. So we're telling, what the North Star for us, what the benchmark was for us before is not the right benchmark. We need a new benchmark. We understood this with discovery of molecules and idea of temperature and vibration and everything. So we then understood, right? Scientists understood that, what we are thinking of, that is not the right way. This is the right way. So on this scale, temperature can be negative. So that is your Celsius scale. It can be negative, but negative temperature does not mean negative kinetic energy. So that's one thing that you need to understand. This makes Celsius unsuitable for gas laws. So we cannot use the negative value of temperature per se, because technically there's no negative value, right? You can either move or not move. So there is no opposite of moving per se, other than not moving. Not moving is the last point, and below that there's nothing, right? So that's what this statement is trying to tell. I hope it makes sense. So moving, the opposite is not exactly not moving. So there's no negative moving is what they're trying to tell. Okay. Not moving is 0. Moving is positive. So there's no negative, right? There's no left of 0. The need for true zero of heat. To describe gas behavior, we need a temperature scale where 0 temperature means 0 molecular motion. Not in this manner. 0 degrees Celsius does not mean 0 vibration. It is not. Right? So 0 temperature should mean 0 molecular motion, and the temperature increases are proportional to molecular energy. It should reflect that. So the Celsius scale cannot do this. And then comes your absolute temperature scale. Absolute temperature is the temperature measured from absolute 0. Absolute 0, that is 0 Kelvin. So we need to understand what is absolute 0. That is 0 Kelvin. The temperature at which molecular motion is minimum, extrapolated from gas volume versus temperature plot. So we did this exclusively in the last video. So it turns out to be at 273.15 degrees Celsius minus. So let me explain what this means. So we studied this in the last video, right guys? Let me go to we studied this, is it not? Okay. So I plotted to this point. I told there is negative temperature also. But if I continue this plot, if I continue this, right? Somewhere it has to touch the x-axis. Okay. So if I happen to do this with many possibilities, right? With many gases, all of them are going towards one particular value, literally. Okay, yes. All of this will go to one particular value. You take up any graph, the temperature goes to this one particular value. Right, even this is a different graph, my bad. This is a volume temperature graph. What we're talking about is pressure temperature graph. But it doesn't matter. So all of them go to one particular value. And this confirms the scientist understanding or reasoning that yes, there's a one particular temperature where things stay still. That's a dramatic way to talk about it. The temperature at which molecules motion is minimum, and that's your absolute 0. And that's how scientists were able to figure out, yes, we have such a value. Now, your Kelvin scale. Absolute temperature is measured on Kelvin scale. Starting from 0 Kelvin, that is absolute 0, never negative. There's no negative value for Kelvin scales. Like, you have degree Celsius scale and Fahrenheit scale. Here we have Kelvin scale. So Kelvin, every degree Kelvin is the same size as the degree Kelvin. So because of this, there's a simple mathematical relationship, and that's this. So this statement, every degree Kelvin is the same size. That is, if I happen to keep a Kelvin scale and a degree Celsius scale, right? Say this is some value x, okay, degree Celsius, and this is say a Kelvin. Now after some distance, you have x plus 1 degree Celsius. This will be a plus 1 Kelvin. So there's a equal gap. So basically the common difference is same. So if this happened to be, say, some x plus 94 degree Celsius, this will be a plus 94 Kelvin. That's what that statement means. Okay. And I think I have one more slide. Why gases need absolute temperature? Gas law relates volume, pressure, and temperature. We have seen that. To measure kinetic energy. Since kinetic energy cannot be negative, temperature used in gas equation must also never be negative. This is why Kelvin absolute temperature is required. And here there are valid only if T is in Kelvin. So this particular PV squared nRT is valid only if T is measured in Kelvin. So we don't write this as small t, we always write it as capital T, indicating the same. I just want to make this point. So in PV is equal to nRT, this has a special name. Sorry, I should have mentioned it over there. See to that you guys write it. Okay, so there's a lot of distraction over here. Let me actually remove all of that. I mean, everything else is same thing. So as in, let's not go to that. So in PV is equal to nRT. I want to make an important point over here. So this T is known as absolute temperature, or is another name, thermodynamic temperature. Okay guys, so this is always measured in, you need to understand this, always measured in Kelvin. Okay, so this you have to keep in mind. Not any other scale, it has to be in Kelvin, right? So that is one thing. I think I didn't miss anything. So guys, so I started the discussion with gases, and we're not actually studying much about gases. All of this discussion was to lead towards absolute temperature. To discuss this particular T value, honestly, we came from that point. So we started with this PV is equal to nRT to discuss about temperature, this T. Here I didn't exclusively mention, but now I'm mentioning all of this. We went through all of this cycle. We went through this fact that for constant volume, how pressure and temperature are related, and how at constant pressure, volume and temperature can be related. All of that can be understood mathematically, right? And then we went on to gas expansion and why it expands uniformly. And we went on to talk about thermometer, and we discussed how to build a thermometer. And I gave you guys an example of how do you calibrate a thermometer, right? So we took up one example and we plotted. So we plot it till 0. Okay, so this turns out to be, oh, I didn't realize. This is absolute temperature. I didn't realize when I discussed. Okay, so here you can see we have a 0 and pressure is 0 and all of that. Okay, now I'm looking at it. My bad, I didn't even look at it properly. So I was discussing this as a degree Celsius, my bad. If you got confused, it's on me. So this is absolute temperature. Now also I was like, why is it 0? Then I looked at, okay, the scale is absolute temperature. Now it's right. For a second I was like, oh shit, I have to redo the video again because this was wrong. I thought this was degree Celsius. No, it's degree Kelvin. Okay, then so basically this is not what I meant. This was not supposed to be the graph which I was supposed to be using. Anyways, while discussing, I discussed the way I wanted. Nothing wrong in this. That was what I meant, right? In my discussion, I wanted to use that graph. Anyways, I used it while writing on the screen. Okay. Okay. So when we do all of this, when we do plot it and all of that, so generally we plot it till here. I mean, the graph technically is somewhere over here. This part will be imaginary. That is what is shown here. Sorry. Generally, this is what we do. Okay, 0 degrees Celsius. This is from here till here. All of the graphs should be looking like this. From here till here, as and when you dot it down, we can see that all of them point to the same value. And that's how we are able to figure out something called as absolute temperature. The lowest of values that we can have. Right? Theoretically, that's what we can have. So this goes back to our original definition. This goes back to our definition of temperature. It goes back to our 0th law of thermodynamics. So the very first video of this chapter or this topic is related to this, whatever you're looking at the screen. So our very definition is that temperature is the measure of vibration, the kinetic energy that the molecules have. And at 0 Kelvin, we don't have things moving. And with that as the basis, we have the formulas and everything. Okay. So that was it's like a recap of the entire thing. End of a chapter per se.